the electric potential landscape of a point charge. With the idea of the potential landscape, we clearly need to change our thinking. Now we apply this to the point charge. We've already have calculated the potential field. And we know here that the potential field of a point as a function of r is then 4 pi epsilon r into q minus 0. Now, what we're going to go into here, this is about the physics of pictures. So we are in deep into the physics of pictures. It is the picture that becomes most important. Okay, let's start. So the first thing that we want to do is that we want to plot the potential landscape. And we know that the potential landscape tells the charge how to move. So let's look at this thing. So here we go, pictures now. Let's see. I need to do good spacing on this guy. So just trying to spread things out here. So I know that if I'm plotting the potential, it's going to look something like this. And then this guy is going to be the same thing on this side. So when I look at this, this is the potential right here. And what we know about this is that what we just did is that we plotted that of the point, which is 4 pi epsilon r into q. So here's a couple of things. First of all, we know that this is the forbidden region. No charge can be here. I'm going to copy this because I'm going to need this later. And so when I look at this, here's what I see. The cause of all of this is, of course, a positive charge. This is the point charge, right? This is the point charge creates, is the source, creates this potential landscape. And so one of the things that we see here is that, to remind you here, is that charges can only move along the potential surface. And another thing that you want to really pay attention to is that right here, you're seeing here is that R equals to 0 tells me that the potential of this point here is infinite. And another thing that we should see here is that since we're plotting this, relative to R, we also see is that right here, that at R equals to infinity, the potential of a point is equal to 0. So as before, we have two viewpoints. The two viewpoints are the electric field versus the potential landscape pictures. So this will be the electric field picture. And then this will be the potential landscape picture. So what I'm going to do is that I'm going to plot this field that we have right here, and then I'm going to just clean this up here. So I'm going to drop this potential function, even though we know it's there. So this will tell me about how to do the sizing here. Okay. So what I want to do is first start off with the electric field picture first, because I think that makes the most sense. So what do we know about the electric field picture? We have a point charge, and it's a positive point charge. And what we know here is that we have E fields that point outwards, and we know that this is the field. So now what I imagine is that I have a charge. In this case, it's a positive charge. And so when I look at this charge here, I'm going to say that this is in state 1, and it's moving with. So when I go to the potential picture, I imagine that I have this guy, and it's doing the exact same thing, and it's moving in this direction, and this is, again, the charge number 1. So what do I know about this charge? Well, for starters, it's moving against the field. And as we already know, if you move against the field, there is an increase in electrical potential energy. So when I go over here, what this tells me here is that now this charge is increasing its potential energy. So in other words, as it moves uphill like this, we see that the reason why it increases electrical potential energy because it moves uphill. And that tells us that the potential is positive. It's moving from a low potential to a high potential. Now, let's look at this other one. By the way, I should keep a positive charge here because that is the source of the potential field. Now, I'm going to have a second charge, which is now moving with the field. And so what we know here is that this guy is moving with the field. And we know that this must be a decrease in electrical potential energy. So picture-wise, I now see my charge, which is now at a, if there's a decrease, that means it's starting up at a higher potential, and it's going to move downwards. So when I'm looking at this charge, I'm now starting in this position 2, which is at a higher potential. And we could see here is that now, if it's moving with the field, we're seeing this guy go from the high to the low. Once again, we see here is that this is the high, and this is the low down here. So clearly in this case here, it moves downhill, which then tells us that the potential is now negative. Now, frankly, this is a very sexy picture. I mean, it's beautiful. Look at it. In potential landscape language, it's clear. It it it's clear that excuse me, in potential landscape language, it's clear when a charge increases slash decreases electrical potential energy. And so here's what I imagine here. So if it's going uphill, I'm seeing something like this. And we could see here is that the charge here is clearly going uphill. And it's because it's starting from a low and it's going to a high. So we see that motion going like this. And so if I start to look at this in the language of potential energy, we are seeing that right here. Let's say that it starts off at the bottom. It's this high. And then the work then goes in. And what does it do? It increases its potential energy to a higher value. So in this case, going uphill is an obvious increase in electrical potential energy. But what about coming down? So if I'm coming down like this, then I have my charges that starts off at a high and then goes towards a low. So once again, here's my high, here's my low. So then in the language of energy, we see here is that this guy starts off like this, where I have some potential energy, and then maybe it doesn't go all the way to the bottom, but there's definitely a decrease. We're seeing that we are definitely getting this type of picture here. So then, you know what? It's exactly as this guy right here. So the only difference is that we do what? Instead of going uphill, we're now going downhill. Is obvious because it's going downhill, so it decreased potential energy. So that's the pictures of the positive landscape with the positive charge. Now let's move on to negative charges. Negative test charges are not as clear as positive ones. So I will start with an analogy to show the strangeness of negative test charges. Of course, in positive fields here. So now, here's my analogy. So the first thing I want to do is I want to talk about positive charges first. So when I look at positive charges, what do I imagine? A positive charge, I should say test charge, behaves in a positive potential landscape as a positive skier. So if you're a skier, then you know exactly what, or you don't even have to be a skier. You could be a runner, right? But going uphill causes an increase in electrical potential energy, while skiing downhill is a decrease in electrical potential energy. And that's obvious, right? Look at this. This is what we just did. Negative charges are not that way. Negative test charges are the exact opposite of positive skiers. When they ski uphill, there is a decrease in electrical potential energy. While skiing downhill, there's an increase in electrical potential energy. These guys are anti-skiers, right? They do the opposite. So if you find this very confusing, it is confusing. So now to show you what I mean by that, it's going to look something like this here. So if I was to draw a picture of the potential here, here's what we would see. So I'm gonna, oops, I need to go back and get that picture. I need this guy right here. So the big difference here is that I have an electron. And one of the things that we find here is that now I am changing my charges to be negative. Okay? So in other words, I have a negative charge, and they're going to be moving up and down these hills. So this guy is going to be negative. And so what you're seeing here, as it moves up, the potential actually decreases, not increases. And as it's going down the hill, the potential increases, not the other way around. So how do I make sense of this? Because if I look at the electric field, the charge is moving in the direction. So if I'm looking at this here, I could then come in and start to say, how do I make sense of all of this? And so what we're going to have to do here is that we're going to have to change our picture. So what I would say here is that here's where I'm talking about, prior to this, I was saying like, what do I mean by this? This is what you're seeing right here. This is the anti-skier. If it goes uphill, how could it be losing potential energy? Very counterintuitive indeed. So now what we want to do is that we want to go in and we want to draw a different picture to make sense of what we're talking about. Okay. We can draw a more helpful, effective potential landscape of what the negative test charge sees. The negative sign of the negative charge inverts the positive potential landscape. This is a game changer in interpretation. So let's draw our physics pictures. Physics is the science of drawing pictures here. So what we have here is that now let's go into the electric field picture. And then over here, we're going to have an effective potential landscape picture. And so here's what I'm going to do. If I have a positive charge, then I'm going to have a field that goes like this. That's what this electric field is. So now, what's the equivalent of the electric field in the potential picture? So now I'm going to come like this, and then I'm going to draw my axis right here. So what this guy does here, I'm going to try to draw this nice and big. What it does here is it now inverts the potential function of the point, the negative sign. So then I imagine that if it's now inverted, we're looking at something like this. If it's now inverted, it's got to be coming something like this here. So now it's inverted. So now the forbidden region is out here. And so we then say that this is the so-called forbidden region. And so now this is caused by this positive test charge for the negative charge. So now let's go look at this thing here. Now I have an electron or a negative test charge here. And here it is. It's coming in and it's moving in this direction. So now what I see here is that I can see that this guy now is moving against the field. And when it moves against the field, in this case, there's going to be a decrease in potential energy. So then we're going to have a decrease in electrical potential energy. So now I have my negative charge here, and this guy's going to move to here. So as it moves, we are seeing here that the potential, that the charge is moving from a higher to a lower potential here. And by the way, this is number one right here. So why is this higher? It turns out that this guy right here is going to be what? Less negative. And then this guy is going to be more negative. So it has, because it's a scalar, it's going to have more. It's going to have a more negative value, means that it's actually smaller. Now, if I go the opposite direction, then I have a charge that then is going to be looking like this here. So now what we're seeing here is that this is moving with the field. And as a consequence, this is going to then increase in electrical potential energy. So in this case, we now have the charge starting here and then moving up. So this is number two. So what you're seeing here is that the charge is going upwards like this, and it's moving from what? From low potential to high potential. So now, here's what we're saying here. So as it moves downhill, we now have a potential that has decreased. If it moves uphill, we now see that the potential has now increased. So that is a better picture than the other one here. So then we can start to look at what we've talked about in the previous, with the positive field, is that in potential landscape language, it shows when a negative charge, test charge that is, increases slash decreases electrical potential energy. So if I'm going down the hill, then I'm seeing that I have a charge that's looking like this. So I'm moving in this direction, and it's clear that we are going from a high to a low. So then energy-wise, we can then say that I'm going from a less negative potential to a more negative potential. And as I do that, that is causing a, a decrease in potential energy, right? So we got to be careful here. Look at the bars. So remember, this is less negative. This is more negative. Where up here, we set the potential equal to 0. So in this case, we then say going downhill is an obvious decrease in electrical potential energy. The word obvious may not be such a good word, but if you remember the less negative versus the more negative, then it should look that way. It should appear that way. So now, on the other hand, we're going uphill. So if we're going uphill, we then have my negative charge here. And this negative charge is going in this direction here. So when I'm seeing this, I'm finding here is that I have this potential function right here. And what this potential function is going to do is that it's going to look something like this. I start off with a more negative, right? This guy is more negative, and I'm going to go to a less negative one. So when I'm looking at this again, remember this is more negative, and therefore, if this is less negative, this is an increase. And we could see it in the picture. So here, going uphill is an obvious increase in electrical potential energy. So now we could talk about a negative point charge. So if I have a I can now summarize what we just did for the positive charge. So we can summarize via pictures of the increases slash decreases of electrical potential energy. So remember, it's going to be the same type of thinking. So now we start with a positive test charge. So I'm only drawing pictures here. So what this tells me here is that I have an electric field picture, which, by the way, I think is abstract because you're not seeing anything. And then over here, we're going to have the potential landscape picture. So I have a negative charge, right? Here's my negative charge. And what I know here is that it has a field that points inwards. On this other hand, we have a negative potential here. So when I look at this negative potential here, I'm seeing that this guy, because it's negative, has to, that potential function of this point here is going to be minus q over 4 pi epsilon r. And then in this other situation, we have the symmetry of the field. Uh-oh, that's not what I needed to draw. That is wrong. It's actually out here. And as before, this green here, again, is the forbidden region. So these two are exactly the same because it's the negative charge that was the cause. Here, we also have the negative charge. And what we're seeing here is that this guy right here this is the negative point charge creates this potential landscape. That's what this guy's doing. Just like the negative charge is creating that that electric field. So here we go. Now let's start our process as before. We have a test charge right here. And this test charge is going to start right here. So when I look at this test charge, here's what I'm seeing. It's a positive test charge, and this is number one right here. So what do I see? I see this guy moving with the field. So if this is moving with the field, then what we say here is that with the field, we expect that there should be a decrease in energy. So then that means here there should be a decrease in electrical potential energy. So if I'm looking at this, I have a charge that's now moving down. So it's going downhill. So if it's going downhill, we can see here that that is literally a decrease because it's going from what? It's going from a high to a low electrical potential energy. So in this situation, we then says that because it moves, no, I need more space. So if it moves downhill, we then say that the potential is negative. Exactly what we would say. On the other hand, if I have another charge, which is now going to be down here, this charge is now moving against the field, and I'll call that number 2 here. So what I'm seeing here is that now this is moving what? This is moving against the field. If it's moving against the field, then what we would expect here is that this is going to produce an increase in electrical potential energy. Well, what does that look like in this effective picture here? In this effective picture, we're seeing that this guy is moving uphill, and it's now moving from what? It's moving from a low to a high, causing an increase in potential. So if I was to write this down, I'm then going to say that this guy moves uphill, which then gives me a positive potential. So now I'm going to repeat the process for a negative test charge. So I now have a test charge. So now I'm going to play the same game as I did before. I have 2 pictures. One is electric. The big difference in this case here is that now I can't do the anti-skier type thing anymore. So I'm going to say that this is I'm going to choose the effective potential picture. So because we have a negative charge, the positive charge of the test charge now flips the negative potential. So in other words, because of the sign difference, I now see that I still have my field like this, but now this is a negative. Now, because of the sign difference, the effective picture now goes like something like this here. And so the source of everything, again, because of the positive test charge in this field, what's causing this is this negative charge. So what does it do? It creates an inverted potential field. If we don't do this, then we have to deal with the anti-skier type thing. So here we go. So now I have a test charge that's negative. And this test charge is either going to be with or opposite of the field direction. So in this first case, we can clearly see that this is against the field. So if you're going against the field, that means here that that should be an increase in electrical potential energy. So in this case, we have our negative test charge. It's starting right here, and it's going to go up to here. And I'm seeing that this negative charge, which is number one charge, is going up the hill. So as it goes up the hill, of course, it's going to be an increase because we are moving from a low to a high potential. So it moves uphill, which then says that the potential is positive. On the other hand, if I am going with the field, then what happens is that I'm going to get an decrease in electrical potential energy. So in this situation, we now have this charge that's now going to be moving downhill instead of uphill. And we're seeing here is that the reason why we're seeing this is because, again, this starts off at a high potential and it now goes to a low potential. So as a consequence, as it moves downhill, the potential here decreases. So that's the physics of pictures of potential fields. So to finish this up, mathematically, to calculate potential fields, we use, for discrete charges, we then say that the net potential is then equal to 4 pi epsilon over 1, and then I'm going to look at the sum of all of the q's divided by their radius. Caution. These are scalar fields and do not follow the superposition principle. You got to be careful. And if we deal with a continuous charges. Then the big difference here is that the net field is now going to be 4 pi epsilon, and then we're integrating dq over r, which is exactly the same thing that we did for Coulomb's law. In fact, these integrals are easier because we don't have to worry about direction.